So up to now I explained the maximum power theorem's conditions, then note down the statement. So if any linear network is connected with a load resistor RL, this RL resistor should be variable resistor, then the complete network is replaced with a Thevenin's equivalent circuit here. So in this Thevenin's equivalent circuit, it has one voltage source, Thevenin's voltage source, and this resistance is Thevenin's resistance. Thevenin's resistance is also called as source resistance or internal resistance of the circuit. Thevenin's resistance is also called as internal resistance of the circuit. Then from the maximum power transfer theorem, the statement is like this here: any linear bilateral network, the power dissipation of the load resistor RL is maximum if load resistance is equal to Thevenin's resistance. Load resistance is equal to Thevenin's resistance or internal resistance of the circuit. So the power consumed by the load resistor RL is maximum here. The power consumed by the load resistor RL is maximum if RL resistance, load resistance value is equal to Thevenin's resistance of the circuit. Thevenin's resistance, or it is also called as source resistance or internal resistance of the circuit. Internal resistance of the circuit is R Thevenin's. So I wrote the condition is RL is equal to R Thevenin's. So here just note on this statement here, the power dissipation of the load resistor RL is maximum. This is maximum. The power dissipation of the load resistor RL is a maximum if RL is equal to R Thevenin's. RL is equal to R Thevenin's is nothing but load resistance is equal to Thevenin's resistance or internal resistance of the circuit. So if you want to note down these points here, just pause this video and note down the points and later watch the video. And RL is equal to R Thevenin's, it gives the maximum power. That maximum power is, if RL is equal to R Thevenin's, that is equal to source resistance, then the maximum power formula is V Thevenin square by 4 into RL. V Thevenin square by 4 into RL. So then if RL is equal to R Thevenin's, load resistance is equal to Thevenin's resistance, then the efficiency of the circuit is 50%. Efficiency of the circuit is 50%. If the load resistance value is less than the Thevenin's resistance, if the load resistance value is less than the Thevenin's resistance, efficiency is less than the 50%. And if the load resistance value is greater than the Thevenin's resistance, RL value is more than the source resistance, then the efficiency is also expected is greater than the 50%. If any circuit satisfies the maximum power transfer theorem, then the circuit efficiency is 50%. Here I wrote one more point. If any circuit satisfies the maximum power transfer theorem, the efficiency of the circuit is 50%. So these points are important points from the maximum power transfer theorem. Here I explained conditions, those conditions for DC circuits. Similarly, we have to discuss AC circuits. First we will go through some problems on the DC circuits, later I will explain AC circuits conditions. From the maximum power transfer theorem, so first I am taking one simple problem. So the problem is given like this: one voltage source is connected and the remaining all the resistors and load resistor RL. The problem is given like this here: the power consumed by the load resistor is maximum. The power consumed by the load resistor RL is maximum. Then what is the value of RL? So the power consumed by the load resistor RL, write the point clearly here. The power consumed by the load resistor RL is maximum. The power consumed by the load resistor RL is maximum. Then find RL value. So then determine RL value. So here we have to find out RL. See, to find the load resistor RL, unknown resistance RL value, and to find the maximum power, first remove this load resistor RL from the given network. So remove the load resistance RL because we want here Thevenin's equivalent circuit. So complete network is converted into Thevenin's equivalent circuit. To convert into Thevenin's equivalent circuit, it requires open circuit load terminals network. So that's why here I am taking here open circuit load terminals. So first remove the load resistance RL resistor. Remove that load resistor value. Then the circuit is acts as a open circuit low terminal circuit. So here 4 ohms and 6 ohms and here 3 ohms is there. And this is acts as a 10 volt source. Then find out Thevenin's resistance and Thevenin's voltage of this circuit, means convert the complete circuit into Thevenin's equivalent circuit. So to find that purpose, initially I am finding here Thevenin's voltage. Thevenin's voltage is nothing but VOC, open circuit voltage, voltage across these 2 points. Voltage across these 2 points is Thevenin's voltage, and here voltage across these 2 points is nothing but voltage across 6 ohms. Already we discussed this type of problems in Thevenin's theorem. So because this is opened, the current through this branch is 0 amps. The current through the 4 ohms resistor is 0 amps. Then VOC is open circuit voltage is voltage across 6 ohms resistor. These two are in series, then it gives the total voltage into same resistance by sum of 2 resistances, that is 6 by 9. These 2 resistors here. Voltage across 6 ohms, 6 by total resistance is 6 plus 3, 9. Then directly it gives here, this gives the 2 and here 3. Then 20 by 3 volts. 20 by 3 volts. Similarly, we have to find out Thevenin's resistance. To find the Thevenin's resistance, voltage source is eliminated. Then the voltage source acts as a short circuit. So voltage source is short circuited and draw the remaining circuit as it is here. Then find the resistance between these 2 terminals. This resistance is also called as R Thevenin's, 3, 6 and 4. Now find the resistance in between these 2 points. So 3 ohms and 6 ohms, these 2 are connected in parallel combination. 6 and 3 is parallel, and the equivalent resistance is 2 ohms. 6 into 3 by 6 plus 3. 2 ohms and 4 ohms both are connected in series. Then becomes 2 plus 4, that is 6 ohms. So finally we got Thevenin's resistance and Thevenin's voltage. Then draw the complete network with equivalent Thevenin's equivalent circuit. Thevenin's voltage and Thevenin's resistance. Thevenin's voltage value is 20 by 3. This is 20 by 3, and Thevenin's resistance value is 6 ohms. So the complete open circuit load terminals is replaced with Thevenin's equivalent circuit. Then collect the load resistance here. Load resistance is RL. This resistance is variable value. So according to the maximum power transfer theorem condition, RL is equal to R Thevenin's. RL is equal to R Thevenin's. Then the power consumed by the RL is maximum. So already the given condition is there. Power consumed by the load resistor RL is maximum. Then find RL value. So the power consumed by the load resistor RL is maximum. From the maximum power theorem, the condition explains RL is equal to R Thevenin's. So here RL is equal to R Thevenin's. R Thevenin's value is 6 ohms is there. Then this value becomes here 6 ohms. So if the load resistor value is 6 ohms, then the maximum power equation is V Thevenin square by 4 RL. V Thevenin square by 4 RL. V Thevenin square is 20 by 3 whole square by 4 into RL. RL is here 6. Load resistance value 6. Just simplify this, then you will get the answer. That is maximum power and load resistor RL value. So to find unknown load resistor value, just we have to find out Thevenin's equivalent resistance according to the given circuit. To find the Thevenin's equivalent circuit, first open the load terminals, then find out the equivalent resistance between these 2 points according to the given problem. If the circuit consists only independent sources, remove all the sources, then find the resistance. If the circuit consists any one source is dependent source, then find out V Thevenin's and Norton's current. Then ratio of these 2, V Thevenin's by ISC, gives the Thevenin's resistance. So this is a standard procedure to find unknown resistance, and to find that unknown resistance, load resistance purpose, compulsory we require this condition. So if the problem explains like this: if the power consumed by the load resistor RL is maximum, then find RL, means you have to take this condition. Otherwise this condition is not considered, and this condition is for only DC circuits. If the circuit is DC circuit, we have to apply this procedure. Similarly, we have to discuss with AC circuits, AC circuit conditions, because in AC circuit 3 different combinations are there. So from that we have to discuss some problems from maximum power transfer theorem. So please note down the solution of the given problem. See another problem from the maximum power transfer theorem. According to the given problem, the complete network is connected with the load resistor RL. The power consumed by the load resistor RL is maximum. So here The power consumed with the load resistor RL is here maximum. Then find RL value. So find RL value. To find the RL value, here it requires one condition. That condition is from the maximum power transfer theorem. From the maximum power transfer theorem, the condition explains load resistance is equal to Thevenin's resistance. Thevenin's resistance is also called as internal resistance of the circuit. Internal resistance of the circuit, or we can call it as a source resistance. So the complete load resistance is equal to source resistance. Then the power consumed by the load resistor RL is maximum. This is the condition now. So to find the condition purpose, here first we have to remove the load resistance value. So load resistor is removed here, eliminated. Is eliminated, right? Then immediately we have to find out the Thevenin's equivalent circuit in between these two terminals, or Thevenin's resistance between these two terminals. And here indirectly given the voltage across these 2 points is VAB. And the complete network is connected with one dependent source and one dependent source, one independent source. So if the network consists one dependent source, then the R Thevenin's resistance value is VOC by ISC. Open circuit voltage by short circuit current, or we can write V Thevenin's by IN, Norton's current. Thevenin's voltage by Norton's current. So now we have to find out Thevenin's voltage and Norton's resistance, Norton's current. To find the Thevenin's voltage, here I am assuming open circuit voltage. Open circuit voltage is equal to Thevenin's voltage across A and B terminals. So that is equal to VAB. According to the given problem, VAB is equal to VOC. So I am writing now VAB is equal to VOC, that is equal to V Thevenin's. So to find the analysis purpose, now this part is opened here. If this is open, the current through this is 0 amps here. Because open circuit load terminals, current should be 0 amps. So here current becomes here 0 amps. Then I am finding here nodal analysis, just I am writing nodal analysis at this point. Here I am assuming this voltage is V1 voltage here. This voltage is V1 voltage. So apply the nodal analysis here. V1 minus this branch. V1 minus 5 by 2K plus in this branch V1 by 2K. V1 by 2K, and this complete branch I am taking now. This complete branch, because the current flows through this path is same here. This side current is 0, the complete current is flows through the voltage source and resistance. So this complete path becomes here V1 minus 3 VAB by, so apply nodal analysis at V1 node. At this node, the current through this branch is V1 minus 5 by 2K plus the current through this branch becomes V1 by 2K, and this complete branch I am taking now, because here this voltage source and resistors both are connected in series. So current through this path is 0, now these two are in series combination. So the current through this branch is V1 minus 3 VAB by 1K is equal to 0. So now from this required voltage is VAB, Thevenin's equivalent Thevenin's voltage. The voltage is voltage across in between A and B terminals. So VAB we require here. So now from this, just add out current through this equation is V minus 3 VAB by 1K. Then we want voltage across this one. So voltage across 1 kilo ohm resistor VAB is equal to current into resistance. Current is V1 minus 3 VAB by 1K into resistance of this is 1 kilo ohm. So 1 kilo ohm. 1 kilo ohm it cancels. These two cancels here. Take this 3 VAB this side. Then it gives you directly one representation. V1 is equal to 4 VAB, because here one dependent source is there. If the network is connected with one dependent source, it requires some more extra equation. That extra equation is V1 is equal to 4 into VAB. So substitute that for V1 value is in this equation. Then if you replace all this with take LCM and replace V1 with 4 VAB, it becomes 4 VAB minus 5 plus 4 VAB plus, here this is 1K is there, it is multiplies with 2. So V1 is replaced with 4 VAB, now it becomes 8 VAB minus 3 into 2, 6 VAB is equal to 0. Finally, the complete equation is in terms of VAB is there, then find out VAB. Here 4, 4, 8, 16, 16 minus 6, 10 VAB. So VAB is equal to 5 by 10. So 5 value 5 by 10. 5 by 10 is 1 by 2. This is approximately equal to 0.5 volts. So finally we got VAB is 0.5 volts here. Then similarly we have to find out short circuit current here, because our required value is RThevenin. RThevenin is required. So from the given circuit, RThevenin is nothing but VThevenin by IN. So then find IN, short circuit current. So these two terminals are short circuited. Then the circuit is like this. Here 5 volts voltage source. Just I am drawing here overview. Then 2 kilo ohms resistor. Here one voltage source and here one resistor is there. All these networks, all these elements are connected in between A and B terminals. A and B terminals. This value is 3 into VAB. 3 into VAB. Then according to the given question, our required question is here current through this branch here. Find the current through this branch, short circuit current. That current is like this. So ISC, this is ISC now. If these two terminals are short circuited, A and B terminals are short circuited, here indirectly VAB becomes 0 volts. Short circuit voltage is 0. So A and B terminals, these two are short circuited, VAB becomes 0 volts. Now this branch is 0, then the voltage source is also 0 here. And short circuit parallel resistance is, this is eliminated here. And voltage source VAB value is 0. If you substitute here 0 value, voltage source is acts as short circuit. Then again the complete path is short circuit is there. So short circuit and one more parallel resistor is eliminated. Now the complete circuit consists of one ISC here and one resistor, this one, and voltage source. This resistor value is 2 kilo and voltage source value is 5 volts. This value is 5 volts. Then the complete circuit is acts as one loop circuit. ISC is equal to total voltage by total resistance, that is 2K. This value is approximately 2.5 milliamps. Short circuit current or Norton's current is 2.5 milliamps and Thevenin's voltage is 0.5 volts. Then the Thevenin's resistance is RTH is equal to VTH by ISC. So this is 0.5 by, and that value is 2.5 milliamps. So milli becomes here kilo. 0.5 by 2.5, that becomes 5 by 25. So 5 by 25 is 1 by 5. 1 by 5 kilo ohms. 1 by 5 kilo, 1 by 5 is also called, the value of the 1 by 5 is 0.2. 0.2 is 200 ohms. Now finally we got Thevenin's resistance is 200 ohms. If the Thevenin's resistance is 200 ohms, from the maximum power transfer theorem, so the maximum power consumed by the load resistor RL is, if RL is equal to R Thevenin's, then RL value is here how much? 200 ohms. According to the given problem, here RL is 200 ohms. This is another problem with the dependent source. So with the dependent source, how to find out the Thevenin's resistance and how to find out the load resistance from the maximum power transfer theorem. So please note down this solution.
Thank you very much guys for watching all the videos. So far what we have completed, let's discuss about it now. Over the screen you can watch Symeta.in app. If you open the app guys, you are going to see there. Let's talk about the store now. In some other branch, let's open a EEE branch guys. In the EEE branch you can see the content. In the content engineering, in the engineering we have electrical circuit, 75 videos there. In that mesh and nodal analysis, if you open, you can see there we are having around 11 lectures guys that we have completed. Then practice set 1, practice set 2 with solutions, questions with solutions, practice set 3, questions with solution, previous ESET questions with solutions, and at last we have what mesh and nodal analysis practice sets. So what we have covered guys, we have completed all the basic to advanced level video lectures. Then we have completed the practice set 1, set 2, set 3. Each set is going to have around 20 to 100 questions there, guys. Based upon the topic marks, it is going to be there in the not only in ESET but also in the government jobs and PSUs. And at last, you have there an online test examination also, in order to check the time management, what you need to utilize in the competitive examinations. So this is so far we have completed, guys. Now you can watch over the videos. It can be utilized for, it is useful for not only the ESET examination but also for DRDO, sub engineer, assistant engineer, Telangana State Public Service Commission, Andhra Pradesh Public Service Commission, BHEL, NTPC, IOCL, Staff Selection Commission, JEE. I remind, guys, for ECEEE and civil, this SSC JEE will be there every year twice. So make sure you utilize all the video lectures to prepare for this examination also. And everyone knows about the Railway Recruitment Board Junior Engineer and as well as ISRO, guys. If you people are interested to watch all the full length videos in the SciMethod.in app, make sure you save this number. This is in charge Sir Shashikant Valmiki sir number, guys, 98486-92598. Give him a missed call, give him a call, guys, for any details, for any updates. Every single day we are updating the videos, material, and as well as what a competitive level examination practice set papers also. Thank you very much, guys. I wish that you have watched all the videos. If you haven't watched so far, go and refer all the videos, guys. Thank you very much. This is Mohammad Inzamam signing off.